Monoidal categories and their representations. Lecture 3. Monoidal functors and strictness. We start from the definition of a monoidal functor. Let C be a monoidal category. This means that we have a category C, a tensor product by functor on it, we have fixed an identity object, and we have the associator and two unitors. Assume that we have another monoidal category C tilde with the corresponding structure denoted by the same symbol as for the category C, but with an additional tilde. Definition: a monoidal functor from C to C tilde is a tuple which consists of a functor f from C to C tilde, a natural transformation eta from the bifunctor given by tensoring in the category C tilde of the two images of f to the bifunctor given by applying f to the tensor product in C, and an isomorphism phi from the identity object in the category C tilde to the image of the identity object in the category C under F. This datum is supposed to satisfy the following conditions. They are given by the three commutative diagrams which will appear on the next slide. So here is the first commutative diagram. For any objects x, y, and z in C, the following diagram should commute. So we start from the tensor product inside C tilde of f of x and f of y, and then we tensor this with f of z. To this object, we can apply the associator in C tilde and end up in the tensor product of f of x with the tensor product of f of y and f of z. Alternatively, we can apply our eta tensored with the identity on f of z and end up at f of x tensor y tensored with f of z. Here again we can apply eta now for x tensor y and z, and we end up in the image under f of x tensored with y and then tensored with z. Here we can apply f of the associator in C, and we go to the object f of x tensored with y tensor z. So here is the second road. We already went to f of x tensored with f of y tensor f of z. Now we apply the identity on the first factor and eta on the second and the third, and we end up in the tensor product of f of x with f of y tensored z. And here we can apply eta for x and y tensor z, and we also end up in f of x tensored with y tensor z. So this diagram should commute. So this is a diagram for the associators. Here are the axioms for the unitors. For the right unitor, we can start from f of x tensored with the identity and apply the right unitor to go to f of x. Alternatively, we can apply the identity tensored with phi to go to f of x tensored to f of y. Here we can apply eta for x, I to go to f of x tensored with I. And here we can apply f of the right unitor in C, and we again go to f of x. So such a diagram should commute. And we have a similar diagram for the left unitor, where basically the right unitor is replaced with the left unitor, and f of x and the identity are swapped. So a monoidal functor is a triple which consists of the functor f and the natural transformation eta and an isomorphism phi, which satisfy these three conditions given by these three commutative diagrams. Now, that was the classical definition, and in the book of EGNO, the definition is slightly simplified. The definition in the book defines a monoidal functor as a pair f, eta, where f and eta are as before, with eta being an isomorphism. Then they assume that f of I is just isomorphic to I tilde without choosing that isomorphism explicitly. And then they require that the first big commutative diagram holds. And they call this big commutative diagram the monoidal structure axiom. One can actually define a canonical morphism between the identity in C prime and the image of the identity in C under F using the following commutative diagram. So we start from F of the identity tensored with the identity. Then we use the right unitor to go to F of the identity. Alternatively, we can go using the identity tensored with phi to f of I tensored with f of I. Then we use eta to end up in f of I tensor I. And then we go to f of I, applying f to the right unitor in I. So since all maps in this diagram are isomorphisms, this uniquely determines phi. So in reality, this is one of our axioms, but only specialized to the case where x is equal to I. So using this diagram, we can choose a canonical morphism from I tilde to f of I. And then the point is that the unitary axioms for monoidal functors follow from this choice. So if we want to compare the classical definition of a monoidal functor and EGNO's definition, then it's obvious that the classical definition implies the EGNO definition. Conversely, we need to prove that the two commutative diagrams related to the unitality hold if we assume EGNO definition. So we prove the diagram for the right unitor, and for the left unitor the proof is similar. And of course, it is enough to prove the diagram for x replaced by x tensor the identity, because tensoring with the identity is a self-equivalence of our category C. Here is a sketch of that proof. So we start from the diagram for the identity which was used to define the map phi. We start from this diagram and we apply to it tensoring with respect to the category C tilde with f of x. And we get the commutative diagram where we now have f of x tensored with f of I tensored with the identity, and then f of x tensored with f of I tensored with f of I, f of x tensored with f of I, f of x tensored with f of I tensor I. So in this diagram, we can look at the first row and the second row. And in the first row, we see that we can apply the associators and transform the first row into f of x tensored with f of I first, and then tensored with the identity, and respectively f of x tensored with f of I, and then tensored with f of I. Now we can use eta and the axiom of the monoidal functors and relate this to f of x tensor I, tensored with I tilde, and f of x tensor I, tensored with f of I. And again, using the axiom of the monoidal functors, the second row, here is the second row, we have a tensor product in C tilde. So using eta, we can rewrite the second row as f of x tensor I and f of x tensor I tensor I. And applying the associator to the last term, we can rewrite f of x tensored with I tensor I as f of x tensor I tensor I. And then we collect all this into one big diagram, and using all the axioms, one shows that the diagram commutes. And one quadrangle in that diagram is exactly our axiom for the right associator for the object x tensor I. And this completes the proof. So EGNO's definition of a monoidal functor is equivalent to the classical definition of the monoidal functor. So here are some examples. The most natural example of a monoidal functor is a forgetful functor. That is a functor which forgets some part of the structure. For instance, let G be a finite group and K a field. Consider the monoidal category G mod of all finite dimensional G modules over K. So this is a monoidal category with respect to the usual tensor product of G modules. And we also can consider the monoidal category of all finite dimensional K vector spaces, again with respect to the usual tensor product of K vector spaces. Note that the tensor product of G modules is actually the tensor product of K vector spaces, but with some additional structure, an action of G on it. So we consider these two categories with a standard monoidal structure on both, and then the functor, which forgets the additional G module structure on the tensor product of two G modules, and just leaves the tensor product of the underlying vector spaces, is a monoidal functor for obvious reasons. This can also be generalized. If H is a subgroup of G, we have the monoidal forgetful functor from finite dimensional G modules to finite dimensional H modules. Another example is the so-called free functor or free construction. Consider the monoidal category of sets, where the monoidal structure is given by the disjoint union and the identity object is the empty set. So here the associator and the uniters are the obvious maps. Let R be a ring. Then we can consider the monoidal category of all R modules with respect to the direct sum as a tensor product and the zero R module as the identity object. Now we define the functor curly f from sets to R modules, which sends a set X to the free R module over X, or a free R module with basis X. This functor is defined in the obvious way on morphisms. And this functor is easily seen to be monoidal. If R is a commutative ring, we can similarly define a monoidal functor from the category of sets, where we define now the tensor product as a direct product of sets, and the identity object is just a fixed singleton, to the monoidal category of all R modules, now where the tensor product is tensoring over R, and the identity object is the regular R module R. Let us now also briefly discuss some variations of the notion of a monoidal functor. The most general analog of a monoidal functor is the notion of a lax or oplax monoidal functor. The lax and oplax monoidal functors are dual to each other. The lax monoidal functor is defined similarly to the usual notion of a monoidal functor, with only difference that the structure map eta from F tensor F to F of the tensor product is not assumed to be an isomorphism, just a natural transformation. And also the map phi from the identity in C tilde to F of the identity in C is not assumed to be an isomorphism either, just some homomorphism. Usual monoidal functors are then a special case of lax monoidal functors, and they are usually called the strong monoidal functors in this terminology. And then we also have strict monoidal functors, and these are the monoidal functors where the structure maps eta and phi are assumed to be given by the identity maps. Let us now briefly discuss morphisms between monoidal functors. So let C and C tilde be two monoidal categories. Let F and F hat be two monoidal functors from C to C tilde. A morphism from F to F hat is a natural transformation xi from F to F hat, which satisfies the following two conditions. Xi, evaluated at the identity object at C, should be an isomorphism, and the following diagram should commute for all x, y in C. So we start with the tensor product of f of x and f of y. We can apply eta to go to the f applied to the tensor product of x and y. And now we can evaluate psi at x tensor y and go to f hat applied to x tensor y. Alternatively, we start from f of x tensor f of y. We apply the tensor product of psi x and psi y to go to f hat of x tensored with f hat of y. And then we apply eta hat to go to f hat of x tensor y. So this diagram should commute. And this diagram looks quite natural. However, the condition that psi of the identity should be an isomorphism maybe is a bit controversial. However, here the correct intuition should be that if we have a homomorphism of unital algebras, we always assume that the identity of the first algebra is sent to the identity of the second algebra. And this is the intuition which is behind the requirement that psi evaluated at I should be an isomorphism. Next, let us discuss composition of monoidal functors. Let C tilde, and C2 tildes be three monoidal categories. Let F be a monoidal functor from C to C tilde, and let F hat be a monoidal functor from C tilde to C2 tildes. Then we have a monoidal functor from C to C2 tildes, which is given by composition of F hat after F, where now the two additional pieces of structure are obtained as follows. So the natural transformation eta for this composition is defined as the composition of f hat applied to eta for f and after eta hat evaluated at f. And the morphism phi for this composition is defined as f hat applied to phi composed after phi hat. So let us check that this tuple satisfies all the axioms of the monoidal functor. So in fact, we will check one of the axioms related to one uniter, and the remaining axioms will be an exercise. So consider the following diagram. So we take an object x in category C, and we consider the corresponding uniton diagram. F of x tensored with the identity goes to f of x tensored with f of the identity, and then this goes to f of x and f of x tensored with the identity. We take this unitor diagram and we apply to it the functor f hat. So we get the corresponding quadrangle f hat applied to the unitor diagram for f. Next, we also have three additional vertices. So we take f hat applied to f of x tensored with f hat applied to the identity in C tilde. We have f hat applied to f of x tensored with f hat applied to f of the identity in C. And we have f hat of f of x tensored with the identity in C two tildes. So from the latter, we have the right unitor morphism to f hat of f of x. And we also have from f hat of f of x tensored with I two tildes, we have the identity tensored with phi tilde, the morphism which goes to f hat applied to f of x tensored with f of the identity. From here, we can apply eta hat to go to f hat of fx tensored with the identity, and we can apply f hat of the identity tensored f hat of phi to go to f hat of f of x tensored with f hat of f of I. And here we can apply eta hat to go to f hat applied to f of x tensor f of the identity. So we have such a big diagram. Directly from the construction, the outer quadrangle commutes because it's the image under f of hat of the right unitor axiom for f. The upper triangle, this triangle, commutes because eta hat is a natural transformation. So we have eta hat here, and then two horizontal arrows connecting this into a quadrangle, and we see that the fact that eta hat is a natural transformation implies commutativity of this square. Now the left quadrangle which we have here, it commutes simply because of the right uniter axiom for the functor f hat. And this means that the whole diagram commutes. In particular, we have this hexagon here, which commutes. And if we look at this hexagon, then the composition of this vertical and this horizontal map is identity tensored with exactly f hat of phi after phi hat. And this was our definition for the map phi for our composition. And similarly here, we have the composition of f hat applied to eta composed after eta hat evaluated at f. And this was our definition for eta with respect to the composition of f hat after f. So then we have this quadrangle, and this exactly establishes the right uniter axiom for the composition of f hat and f. So now we know how to compose monoidal functors. Let us now briefly discuss monoidal equivalences. Let C be a monoidal category and C tilde another monoidal category. Let F be a monoidal functor from C to C tilde. We say that F is a monoidal equivalence provided that it is an equivalence between the underlying categories. One good example is, of course, that the identity functor is a monoidal equivalence. And a negative example is that forgetful functors, for example, from G mod to vector spaces where G is a non-trivial group, they're usually not monoidal equivalences, simply because they're not equivalences of categories. Next, let us talk about inverse monoidal equivalences. Let F be a monoidal equivalence from C to C tilde. Let G be a right adjoint to F. So since F is an equivalence, it follows that G is actually a bi-adjoint to F, so it's just an inverse equivalence. So we claim that the functor G can be given a natural structure of a monoidal functor. So let alpha be the adjunction morphism from Fg to the identity on C tilde. Let beta be the adjunction morphism from the identity on C to Gf. So since f and g are inverse equivalences, alpha and beta are in fact isomorphisms. Now we define the map phi hat from the identity in C to G applied to the identity in C tilde as the composition. So we start from the identity in C, we apply beta, and we go to Gf applied to the identity in C, and now we apply G of phi inverse and end up in G applied to I tilde. So this composition is our phi hat. Next, we define the natural transformation eta hat from G tensor G to G of the tensor product via the following composition. So we start from G of x tensor G of y. So we can apply beta and go to Gf applied to this composition G of x tensor G of y. Since f is a monoidal functor, we can apply G of the corresponding eta inverse, and we end up at G of f of G of x tensor with f of G of y. And now here we can apply G of alpha evaluated at x for this factor and alpha evaluated at y for this factor, and we end up at G applied to x tensor y. And it is not difficult to check that G end out with this additional structure of eta hat and phi hat is in fact a monoidal functor. So this construction comes from the paper by Kelly, which is called Doctrinal Adjunction, which appeared in 1974. So one can look at that paper for more details. But the main message is that the inverse equivalence for a monoidal equivalence has the natural structure of a monoidal functor. So we will use this shortly when discussing the strictification theorem for monoidal categories. So what is a strict monoidal category? Assume that we have a monoidal category. We will say that this monoidal category is strict, provided that for all objects x, y, and z in this category, the tensor product of x and y tensored with z is equal to the tensor product of x with y tensored with z. And also, the tensor product of x with the identity object on any side is equal to x. And finally, the associator and the unitors are all given by the identity maps. For example, the category of all endofunctors of a fixed category, where the monoidal structure comes from the composition of functors and the identity object is the identity endofunctor, this category is strict. And the connection between monoidal categories and strict monoidal categories is given by the following strictification theorem by MacLean. Every monoidal category is monoidally equivalent to a strict monoidal category. This means, given a monoidal category C, there exists a strict monoidal category C tilde and a monoidal equivalence F from C to C tilde. To prove this theorem, we will define C tilde as the category of certain endofunctors of C. And that will be strict by the example from the previous slide. And the intuition how we construct C tilde comes from the fact that if you have a monoid M, then this monoid is isomorphic to the monoid of all maps from M to M that commute with right multiplication. So let's discuss the proof of MacLean's theorem. We start by constructing the category C tilde. So we define objects of C tilde as pairs consisting of a functor f from C to C and a natural isomorphism gamma, which when we evaluate to x, y, where x and y are objects in C, gives us a morphism from f of x tensor y to f of x tensor y. So this morphism is assumed to be an isomorphism. And this datum is subject to the following conditions. For all x, y, and z in C, the following pentagon diagram should commute. So we can start from f of x, tensored with y, and then tensored with z. We apply the associator to get to f of x tensored with y tensor z. And now we can apply gamma and end up at the object f applied to x tensored with y tensor z. Alternatively, starting from f of x tensored with y and then tensored with z, we first apply gamma for the first factor and end up at f of x tensor y, which is then tensored with z. We apply gamma again, we end up at f of x tensor y tensored with z, and now we apply f of the associator and we end up at the object f of x tensored with y tensor z. So this diagram should commute for all x, y, and z in C. Let us now define morphisms in C tilde. A morphism theta from the pair f, gamma to f tilde, gamma tilde is a natural transformation theta from f to f tilde, such that the following square commutes for all objects x and y in C. So we can start from f of x tensored with y and use gamma to go to f of x tensor y. From f of x tensor y, we can apply theta to end up in f tilde of x tensor y. Alternatively, starting from f of x tensored with y, we apply theta tensored the identity to end up in f tilde of x tensored with y, and now we apply gamma tilde and we end up in f tilde of x tensor y. Composition of morphisms is just the usual composition of natural transformations. So now we want to turn C tilde in a tensor category. So we define the tensor product of f and f tilde as the composition of f and f tilde, and then the structure morphism xi is given by the following composition. So we start from f of f tilde of x, and we answer this with y. We apply gamma to go to f of f tilde of x tensor y, and now we apply f of gamma tilde to go to f of f tilde applied to x tensor y. This is very similar to how we discuss the composition of the monoidal functors. So this definition is very similar to the definition which we applied there. And we define the tensor product of morphisms simply using the usual composition of natural transformations. The identity object will be, of course, the identity functor, where the structure morphism associated to it is given by the identity maps. And then it's easy to check that this makes C tilde into a strict monoidal category. Now, for any object x in C, we consider the endofunctor Lx given by the left multiplication with x. Then, this endofunctor Lx, together with the structure morphism, which is given by the associator alpha, in which the first index x is fixed, and then the second and the third indices vary. This pair belongs to C tilde due to the pentagon axiom. So the defining axiom for an object in C tilde, if we replace f by Lx, this simply gives us the pentagon axiom. So this is satisfied. For each morphism f from x to y, we have morphism theta f from Lx to Ly, which is given by tensoring with f on the left. This defines a functor from C to C tilde, and the claim is that this functor is in fact a monoidal equivalence. So let's sketch the proof of this claim. Given some morphism theta from Lx to Ly, we define f as the composite of the following morphisms. So we start with x, we apply the inverse of the right uniter to go to x tensor the identity. Now we can apply the evaluation of theta at the identity to go to y tensor the identity, and now we apply the right uniter of y, and we end up with y. So this composition we denote by f, and then it is easy to see that theta is actually given by tensoring with f on the left. In particular, this means that our functor L is full. Next, given a pair f comma gamma in C tilde, it is easy to check that this object is isomorphic to the object of C tilde given by left tensoring with f of the identity, which implies that our functor L is also dense, or essentially surjective. Next, evaluated at the identity object, one shows that the functor L is faithful. So it's full, dense, and faithful, and hence it is an equivalence. And finally, we need to show that L is actually a monoidal functor. So there is a natural monoidal structure on L, which is given by the following maps. The map phi from the identity to tensoring with the identity on the left is given by the left uniter, or the inverse of the left uniter. And the natural transformation eta from tensoring first with y and then with x to tensoring with x tensor y is given by the inverse of the associator. And then it is easy to check that all axioms are satisfied. This is a good exercise. Here are some other problems and exercises. Question 1. In the claim that the EGNO definition for a monoidal category implies a classical definition, check all details in the proof of the first commutative diagram. Question 2. In the claim that the EGNO definition for a monoidal functor implies the classical one, prove with all details the second commutative diagram. Question 3. Is a left-right adjoint of a monoidal functor automatically a monoidal functor? That's a very interesting question to think about. Question 4. Given two mutually inverse monoidal equivalences, check that the adjunction morphisms are morphisms of monoidal functors. And question 5. Check that theta is equal to tensor inverse f on the left in the proof on the previous slide. Thank you very much and see you next time.